Hello everyone, thanks for watching this video today, and in this video we're going to talk about finding Taylor polynomial approximations of functions. Before we actually find approximations, we should probably make sure we know how to find Taylor polynomials. And before we do that, let's take a look back at some things we did earlier in the year, like linear approximations. Okay, now this is something that obviously people needed to do before the invention of the calculator. And that every mathematician had a calculator in their hands. They needed to do things like this, linear approximations and Taylor polynomial approximations, to get approximate answers if we couldn't find an actual answer from a function. So let's recall back in topic 4.6, we learned that if a function is differentiable at a point, then it can be approximated near that point by its tangent line, which we call a linear approximation. Tangent line, and then the cell for L of x, we wrote that there. Because this linear approximation is the first degree polynomial, we named it, well, we can name it now, P sub 1 of x. This polynomial has some very important properties. One, it matches the function f and the value at c. And two, it matches the function f and the slope at c. The problem is that linear approximations don't always work well when the graph of f has a great deal of curvature near c. Take a look at this graph here. If I wanted to find an estimate for this point right here, well, that's pretty close to the tangent line, so that's going to be a pretty good estimate. What if I want to find the estimate for this point right here? That's pretty far away, and that estimate's not going to be very good. Okay? To fix this, we create a quadratic approximation by using a quadratic approximating polynomial by adding one new term to that linear polynomial. We can denote this new polynomial P sub 2, and it looked like this. Y value plus slope times x minus c plus a quadratic piece at the end of that. Notice that we will need to find the value of the coefficient a. To determine a and to ensure that P sub 2 of x is a good approximation for f near point C, we require that P sub 2 of x agree with f in value, slope, and concavity at C. In other words, P sub 2 must satisfy all three of these conditions. The first one, that the y values are the same, again, just like before. The second one, that the slopes are the same, again, just like before. And this new one, that the concavity is also the same. So therefore, our new quadratic is y value plus slope times x minus c plus this new quadratic piece. So therefore, a would be equal to f double prime of c over 2. Bear with me. We're getting somewhere really important in the future. All right, right now, let's just take a look at a linear versus a quadratic approximation for the natural log of x. All right, so if I wanted to find a linear approximation, this is back from unit 5, like I said here. All right, how do we find a linear approximation? We want to write a tangent line out, right? So our tangent line here is, let's do the slope. So f prime of x would be 1 over x. F prime of 1 would be 1 over 1, which is 1. And f of 1 is ln of 1, or 0. Okay, so we can call it P sub 1 of x would be equal to 0 plus 1 times x minus 1, or we can just write it as x minus 1. So that's our linear approximation. A quadratic approximation now, so P sub 2 of x is going to be that same first couple steps, so f of c plus f prime of c times x minus c, plus, we just discovered, f double prime of c over 2 times x minus c squared. Okay, so now we already have a couple of these things taking place here, but basically what we want to do is we need to find f double prime of c. So remember, f prime was 1 over x, then f double prime will be negative 1 over x squared, right? So f double prime of 1 would be negative 1 over 1, or negative 1. So using this formula that we came up with above, my equation here could be p sub 2 of x equals f of 1, which we already said was 0, plus f prime of 1, which you already said was 1, times x minus c, plus f double prime, which is negative 1, so I'm going to change this to minus 1, over 2 x minus c squared. And that would be my second degree. This is actually called a second degree Taylor polynomial, but for right now we just call it a quadratic approximating polynomial. And yes, we can continue simplifying this. So it'll just be x minus 1 minus 1 half x minus 1 squared. I don't know why I put c here. Sorry about that. It's supposed to be a 1. Okay. And then it says, use the approximation to estimate the value of natural log of 1.05. So P1 of 1.05 would just be 1.05 minus 1, or 0.05. P2 of 1.05 would be 1.05 minus 1, which is 0.05, minus 1 half times 0.05 squared, which we can use a calculator to do that for us. I'm getting 0.04875. How do these compare to the actual value of natural log of 1.05? So natural log of 1.05, you put that in your calculator, is going to be 0.04879. So while this is pretty close to that, it's off by 2 thousandths, look how close this quadratic approximation is. Now we're talking about 400 thousandths of being off there. So really, really close. The big question is, can we extend the idea of linear quadratics that will approximate functions to higher degree polynomials that can perhaps be better at approximating these functions? And of course, in math, the answer is yes. These are called Taylor polynomials. All right? So here we have our first degree Taylor polynomial. This is called a second degree Taylor polynomial. So it's only logical that our third degree Taylor polynomial would take the second degree one and add on a cubic b in front of it. And then what would have to be true is that p, the third derivative of 3, would have to equal f triple prime at that number. Okay, because p sub 3 is built using p sub 2, the first 3 conditions are already met. The last condition, we have to make sure these are equivalent. So we set p prime of 3 equal to all this, and then p double prime of 3 equal to all this. So then p triple prime of 3 would just be this right here. In other words, it's 3 factorial times b. So p triple prime has to equal 3 factorial times b, and if we do some maneuvering, b would have to equal to f triple prime over 3. So you might start to see a pattern developing here. And here we have an nth degree Taylor polynomial formula. F of c plus the first derivative times x minus c, plus the second derivative over 2 factorial times x minus c squared, plus the third derivative of c over 3 factorial times x minus c cubed. And then you keep going until you get the nth degree derivative over n factorial times x minus c to the n. That's called our nth term Taylor polynomial for f centered at c. A special case of this, so remember back when we did mean value theorem and Rolle's theorem, we had the mean value theorem, and a special case of mean value theorem was Rolle's theorem. Same thing here. A special case of Taylor polynomials is called the Maclaurin polynomial. If c is equal to 0, then we can simplify that down to just that, which is pretty obvious just by putting 0 in everywhere you see a c. But that's just called the Maclaurin polynomial. Okay, so it says find a 7th degree Maclaurin polynomial. All right, so I'm going to go ahead and just write some stuff down here first. First of all, n equals 7, that's 7th degree. Maclaurin tells us that our center is 0, so c equals 0. And our function is sine x. So I'm going to go ahead and just start that by writing down my Maclaurin polynomial here. So now we're going to do p sub 7 of x equals f of 0 plus f prime of 0 times x minus c, which is x minus 0. If you don't want to write x minus 0, you just write down x, that's fine. Plus f double prime of 0 over 2 factorial times x squared. Again, it's x minus 0 squared, but just x squared for now. Plus f triple prime of 0 over 3 factorial times x minus c cubed plus the fourth derivative at 0 over 4 factorial times x to the fourth plus the fifth derivative at 0 over 5 factorial times x to the fifth plus the sixth derivative at 0 over 6 factorial times x to the sixth. Finally, plus the seventh derivative at 0 over 7 factorial times x to the seventh. So this is called a 7th degree Maclaurin polynomial. Okay, and now we just kind of fill in the rest of it here. So f of 0, so sine of 0. And I actually should have put this is x here. I should have put all these as x. Because we called it x, we want to stay consistent with our notations here. So let me just fix these last two and then we'll get on to the rest of the problem. Okay, so now we're going to put 0 in everywhere we see an x. All right, and what that's going to do is that's going to create lots of different pieces to our polynomial here. So we're going to do f of 0, which is sine of 0, which is 0, plus the first derivative at 0. So the first derivative at 0, so let's just take our first derivative over here, f prime of x equals cosine of x. I'm going to take the first 4 derivatives, so we have those ready to go. All right, that's just going to repeat from there. All right, so the first derivative cosine of 0 would be 1 times x, okay? And then plus the second derivative at 0, so the second derivative would be negative sine of 0, which is 0 over 2 factorial times x squared, plus the third derivative, which is negative cosine of 0, so negative 1 over 3 factorial, which is 6 times x cubed. And then it just repeats from there. So the fourth derivative would be sine again, so 0 over 4 factorial x to the fourth plus 1 over 5 factorial x to the fifth plus 0 over 6 factorial x to the sixth minus 7th derivative, so that would be negative 1. That's why it's minus 1 there. And then 7 factorial, which I don't expect you to know off the top of your head. You can use your calculators to help with that. It's 40, x to the 7th. So just cleaning this up a little bit, it would be x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 40. And that right there is called the 7th degree Maclaurin polynomial for the function sine of x. Then B, we're just going to use that to approximate sine of 0.2. Okay, so then we're just going to do P sub 7 of 0.2 is going to be 0.2 minus 0.2 to the third over 6 plus 0.2 to the fifth over 120 minus 0.2 to the 7th over 50, 40. Obviously, you can use your calculator for that. And we should be getting about 0.198669. All right, and then if you were to actually take your calculator out and figure out what sine of 0.2 is, let's see what that is here. Sine of 0.2. 0.198669. It's actually the exact same up to the 6 places after the decimal. Okay, it's not as different from there. I think 3308, but you can see how good of a job of estimating this does. And we're pretty close to the C value there. All right, so some things to notice here about the degree of each term. We can make an assumption about cosine of x. Let's just talk briefly about that. All of the degrees of each term are odd for sine because sine is an odd symmetric function. Look at the degrees of x, right? 1, 3, 5, 7. So we could probably assume for cosine, all of our degrees would be even because cosine is an even symmetric function. Probably. We don't know for sure until we actually do it, but it's a pretty good assumption. Okay. Let's do another Taylor polynomial, this time using a table of values. Okay, a function f is differentiable for all orders n and has the following derivative values when x equals 1. Find a third degree Taylor polynomial for f centered at x equals 1. So we kind of have the Taylor polynomial formula written out for us already right there. All right, that's the general one that we would use. For a third degree, so it's going to write down what would a third degree one be here. So P sub 3 of x would be equal to f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared plus f triple prime of 1 over 3 factorial times x minus 1 cubed. All right, so luckily we pretty much have all these numbers ready to go already that we need. F of 1 is 2. F prime of 1 is negative 3, so minus 3 x minus 1 plus 1 over 2 x minus 1 squared minus 6 over 6 x minus 1 cubed. Right. And that's perfectly fine. You know, if you wanted to simplify it a little bit, you can. You don't have to. P3 of x would be good there. And actually, you could even leave this as 2 factorial and 3 factorial if you want it. Since we're not actually doing anything with this, you could stop there and be done with it. Okay, number 4, write a Maclaurin polynomial. So a function g has derivatives of all orders at x equals 0. It is known that g of 0 is 2, g prime of 0 is 1, and g derivative of anything after that would be n squared over n for anything where n is greater than or equal to 2. Okay, and a third degree Maclaurin polynomial. So I'm going to go ahead and start by writing a third degree Maclaurin polynomial's basic form here. So P3 of x is going to be g of 0 plus g prime of 0 times x minus 0, or just x, plus g double prime of 0 over 2 factorial times x squared, plus g triple prime of 0 over 3 factorial times x minus 0 cubed. All right. So let's see here. What do we know? We know g of 0. I don't know why I must have copied this table down. We don't need this table for anything here. This is on the last problem. Get rid of that. I don't want to confuse us with this problem here. Okay. So g of 0, we are told g of 0 is 2. g prime of 0 is 1, so 1x. It's actually supposed to be negative 1. I'll fix this for our notes. This problem is supposed to be negative 1 there. Okay, and then for g double prime of 0 and further, we're going to use this right here. Okay, so g double prime of 0 is going to be n squared over n factorial. So that's going to be n squared over n factorial over 2 factorial x squared plus 3 squared over 3 factorial over 3 factorial x cubed. All right, so we can definitely do some simplification with that. 2 minus x plus, so this is going to be 4 over 2 over 2, which ends up being 1, x squared, plus 9 over 6 over 6, so 9 over 36, or 1/4 x cubed. There's our third degree Maclaurin polynomial for g of x. Okay? If you go to the last slide here, one of the primary goals of studying Taylor polynomials, and then later in a couple days here, Taylor's series is to find a way to represent an ugly function as a prettier function so we can manipulate it much easier, which is kind of what we've been doing all day today. Instead of doing natural log of x or sine of x or something like that, we got these nice polynomials that we can do a lot more with in a lot easier fashion. All right? That'll do it on our lesson today on using Taylor approximations. I hope you enjoyed our lesson, and we'll see you again soon.